Hi everyone, can you hear me? Am I audible? Is my screen visible to all of you?
Yes, ma'am.
Okay, very good. So welcome back to this is I think fourth lecture, right? Fourth lecture of combinatorics. So in the last lecture we mainly discussed about regular polyhedron, right? And we introduced one important and beautiful concept called finite projective planes, right? So in today, basically, we are going to see in more detail regarding finite projective planes. And right, so I hope you have remembered the definition of finite projective planes. So it's though the motivation came from geometry, but it's not limited to geometry, right? So it's basically it's talking about set system. So you have a set of elements, right, and a system of subsets consisting of that set of elements, right? If they satisfy certain properties, then we refer that set system as finite projective planes, right? So to be specific, first property is there should be 4 elements in that set, right? In that set of, I mean, in that in your set of elements, such that no 3 of them are collinear, right? So that's the first property or first axiom, I would say. And the second property or second axiom says if you have you consider any two distinct sets, right, from the set system, then basically they are going to intersect in a unique element, right? So in other sense, intersection with L1 and L2 is actually the cardinality is exactly 1, right? Similarly, if you consider any two distinct element from the given finite set, right? So you can actually consider exactly one line and that line should be there in your set system, right? Okay, and we saw the smallest possible finite projective plane is basically planoplane. We saw this example, and it actually it is we also saw one puzzle, right? It's not the only puzzle. There are several puzzles actually related to planoplane. So I will not enumerate all of them. Right. So today, what is our plan? We'll see more properties related to finite projective planes, and of course, those are combinatorial properties. And the good point is, I mean, to prove those properties, you only need to remember these axioms. Okay. And of course, little bit about of combinatorics, whatever you have that knowledge in your mind, whatever you have learned so far, that pre-exist with using that pre-existing knowledge itself, you can prove. Okay. So in today's discussion, so I will hope that you will answer almost all of the things, whatever we are going to discuss, right? So the arguments and all, I will expect that you are going to give it to me. Okay, so let's start with uh, one good property. So first, let us see one definition. Oval. So what is oval? So consider the planoplane, right? So, right, and you know F, right? F means this F I am talking about, 4 element set satisfying this property, means 4 element set such that no 3 of them are collinear, right? So there should be there might be several such F satisfying this property, right? So I am referring one such as oval, means each of them are oval. So what is oval? Oval in a planoplane, it's with respect to plane we have defined, but one can define with respect to any other plane. So the question is with respect to only planoplane. So that's why I have given one special name called oval. So what is oval? So oval is basically is on the planoplane. It is a set of 4 points such that no line is incident it with it more than 2 of them, means it's a set of 4 points such that no 3 of them are collinear. Okay. So as I mentioned, there could be, so one of you actually gave me one construction of that oval last day, right? In the last class, you have enumerated one oval. So now today we are asking how many ovals are possible for a planoplane. Can you give me the count, or maybe I have written there already. So can you try to prove that there are exactly 7 ovals in a phenoplane? I hope you have understood what oval we are talking. I mean, what is oval with respect to phenoplane? Phenoplane. I mean, oval means the 4 points. No 3 of them are collinear. So there might be several ovals in a phenoplane. So now we are asking about how many ovals are possible in a phenoplane, and it turns out to be that there are exactly 7 oval, not more, not less. Now I am asking you, how will you prove such statement? Can you give me a proof for this? So I hope you have understood what is oval, right? Is there anyone who did not understand what oval is? Okay, my iPad doesn't have more charge. Okay, so I hope the question is clear, right? So question was, there are 7 ovals in a phenoplane. Now the question is, how will you prove it? Give a proof. What is the proof for this? I hope you have understood the question. All of you understood the question. Can you start giving a proof? So how to enumerate oval? Okay, so let's try doing this. So I will start uh, so leveling. So though this graph is already leveled, so let's start drawing this phenoplane once more. Okay, so this is my phenoplane. I have 7 points and 7 lines, right? One line is this one, and yes, I have one line like this, another like this, another like this. This is in the comma intersection. Okay, so uh, let us try to construct one oval out of this phenoplane. So I will level them. 4 vertices, right? So I label them as 1, 2, 3, and 4. Let's say, okay. So let us see how many ways you can actually label, or how many ways you can actually choose construct one oval out of your graph, right? Okay, first see where you can label how many vertices. I mean, you can choose for one. If you are constructing one oval, right, you need to choose one vertex from the given set of vertices, right? So I have 7 choices. So I can actually give label to any of these vertices, right? So there are 7 choice. So 7 option for this position, right? So let's say this is my that one. I can choose any one of them. I have just fixed this as my oval, let's say. Okay, so if I fix this, now the question is, so now if I want to level, give level for the for that oval, the 2, right? So how many vertices we can level for 2, right? Which of the vertices those are actually eligible to become one oval, right? So you can see I have actually remaining 6 vertices, right? So among them, any of them actually I can label as a oval, right? So let's see, let's try to consider that this is my second vertex, right? Which I label as 2, right? So I can actually, after this position is filled, so I can fill this position, second position, by 6. I mean, there are 6 many possibilities for this, right? So I can fill up this with 6. So how about third one? So for the third vertex, so where, I mean, which of the vertices are eligible to become in this oval? How many vertices are eligible for this position?
4.
Right, 4, right? So you can see I have exactly one line, right, passing through this 1 and 2, these vertices. There would be one line, right? And since this is phenoplane, and each of the line you can see has exactly 1 point. So 3 points. So that third point, this point is not eligible for this third position, right? So I have this remaining 4 vertices which are basically eligible for, right? So I have 4 position for them. Okay. So let us fix any of them as my this level 3. So maybe you can choose any of them as I said. So let's give them some color. Right. So which vertex would you like to consider as your oval? Let's say I am considering this, and I have labeled that vertex as the third vertex in my oval, right? So once I have fixed this, now how many way you can fill this fourth position? Can you see? So 1, 2, and 3, they are actually already filled, right? You have filled it correctly. Now, so what are the options available for 4?
Only one option.
Right, only one option, right? So why only one option is there? Because this guy to anyway gone, right? So now if you 1, 3 this pair and also the 2, 3 pair. So for this, for 1 and 3 there is one line, so it contains 3 points. So that point is gone. And if you consider 2, 3, for that pair there exists another line which contains 3 points, and this point is there, that point, so that is also gone, right? So there is exactly 1 point remaining for this position, and this is that. So that's the only option. So you can fill this position by only 4. So now you see. Uh, now can you tell me how many oval is possible in a plane? Can you tell me?
Every oval will be counted 4 factorial times. So
Sorry.
every
Right.
every oval will be counted.
Right. So in this way, you can see that this is actually I have maintained one order, right? So 1, 2, 3, 4 is counted how many times in this counting. So if you are just multiplying blindly 6 times, 4 times 1, right? Then in that count, you are actually for 1, 2, 3, 4, this vertex combination, right? 1, 2, 3, 4, it is you are getting 4 factorial many permutation for them, right? And all of them you are counting in this count, right? So in other words, so you need to actually apply the division rule to count the number of ovals in a plane. That would be just this number, right? Each of this permutation, I mean, actually this is one just to permutation, right? And you are actually counting all these permutation possible. So you are also considering for the same vertices 1, 2, 3, 4, whatever you have drawn. So that will also appear like 4, 3, 2, 1, right? That is also one oval. So you are counting more basically, right? 4 factorial times you are counting one oval, because you have actually, why this is happening, because you have labeled them, right? So but for us the labeling doesn't matter, right? They are not distinct to us, right? So in whatever way it comes, 1, 2, 3, 4, whatever, so it might come 4, 3, 2, 1 or 3, 2, 1, 4, these vertices, it doesn't matter to us, they are not labeled to us, right? So you need to divide it by 4 factorial. So in this way, if you see, then basically 4 factorial means 4 times 3 times 2, right? So this is gone. So you are only left with 7 possibilities. So number of ovals is basically 7, exactly 7, not more than that. Okay, good. So this is, you can actually, here we have not used anything fancy. Using the existing knowledge means elementary concept only, one can do this. Okay, now let's come back to, as I mentioned, all the proofs whatever we have for today's class. You don't need any fancy things. I mean, we're using elementary concept, maybe sometime the properties of the finite projective plane, one can prove things. Okay, now let's try to prove another important property of finite projective plane. So it says, let's say I have a finite projective plane. Okay, now let's consider any 2 lines, okay, from that projective plane. So it will be the fact that these 2 lines, let's say L and L dash, the number of points containing each of them is actually same. Okay. In other words, cardinality of each of the set in your finite projective plane is going to be same. Okay. Can you prove it? Why this is so? Can you prove it? What do you think? How to prove such statement? Okay, here again you need one small trick. Okay, the trick is something like this. So the proof is basically so that way. Okay, will you try first of all? Should I give you some time to prove it, or I should tell you? Anybody? Okay, since everybody is in silence, so let's proceed. So the proof is basically it's a little bit of trick. First, we will show that there exists one element x in the set of elements that doesn't belongs to L, and it doesn't also belongs to L dash. It neither belongs to L nor belongs to L dash. Okay. So first we need to prove that this kind of things is there. If you can prove this, so then basically what I will do. So for the time being I am assuming that there exists one point which actually doesn't belongs to neither L, I mean which or not L, sorry L dash, right? Okay, so if that is the case, so the picture looks like this. I have one x, I have two lines. Of course, they are going to meet. I know that, right? So let's say this is my L and this is my L dash. Okay. So I hope all of you know bijection. So what I am going to do is basically I am trying to make a bijection from each of the elements of L to each so I am going to make bijection. So I am going to map it. Let's say that mapping is 5. So it map L to L dash. Okay. So let's consider some point y in L. Okay. Okay. Now consider the line xy. Okay. There should be one line. Exactly one line, right? And according to our assumptions, right? Now this line should intersect L dash. That is also according to our assumption, and that intersection should happen in exactly one point, right? So let's say that my z is. So what I am doing, so that's my bijection. So what I am going to do is basically I am taking one point y in L, and I am drawing the line xy, and I am projecting, or maybe I am just projecting it to over L dash. Means I am seeing what is the intersection of this line with L dash, and that point is basically that function. Function is actually this. Okay, does it make sense? This function. So now, if you can prove that this is basically it's a bijective function, then you are done, right? Then the number of points in L should be exactly equals to number of points in L dash, and the proof is done, right? Does it make sense to you? So if you want to prove this proposition, so the two main thing is, as I mentioned, so first thing is you need to prove that there exists some point x which doesn't belongs to L and L dash, right? It neither belongs to L nor belongs to L dash. And the function which I defined, that is a bijection. Then you are done. So now let's come back to one by one. So can you prove the first thing first? Means can you prove that there exists one point x which doesn't belongs to L or L dash, right? It neither belongs to L nor belongs to L dash. Can you prove it? That there exists such point which doesn't belongs to L or L dash. So the statement is there exists a point x in this that does not belong, such that you can write such that x doesn't belongs to L and x doesn't belongs to L dash. Can you prove such statement?
It directly comes from the definition, I guess. For example,
Okay, I don't want some guess. Yeah, that's the hint, of course, but you need to give some proof. So how will you prove such statement?
so all the points cannot lie on L. That's sure because of
Uh-huh.
So okay, so let us take all the points that do not lie on. Now all these points, all of these points, if all of these points cannot lie on L dash because that means there exist two lines such that uh,
So how you
like,
prove such thing? Right, right. You are in correct direction. So
so
yes, you need to actually see these properties carefully, right, to prove
okay,
such
so
statement.
okay, so
Yes, go ahead.
yeah, that means all the points uh, all the points are either on line L or they're on line L dash. That means L1 intersection L2 cannot be 1.
L1 intersection L2 cannot be 1. Okay. Okay.
So
Uh-huh. Right. So if okay, so L1 intersection, why I didn't understand. So I might be the thing, some of the points are here in that. So the line is so special. So let's say this. If you take L1, L union L dash, then that will be, let's say, this set X, right? I might happen that all these points are here, and okay, intersection is here, no problem. Then what will be the problem in that case?
I think
And can
Excuse me,
we
ma'am.
take two
Huh,
different points from uh,
right.
so
Go
can we
ahead.
take two different points from L and L dash, and we can say that there exists a line which contains both of these points.
Say that once again. You are going to say that you can take 2 points from L and L dash. Okay. You are going to take 2 points.
Different from
Okay.
this intersection. And then there
Different
exists
from 2 points. Okay. A, let's say B. Then yes,
uh,
and this is
then
the
there
intersection
exists
point is C. Right. Then
then there
yes,
exists a line joining both of them. There exists a
line
line,
joining
I mean
joining
line that
both of
contains
them,
both it.
A and B. Okay. Yes.
And
Then.
then we claim that it cannot contain any other point. Like it has to just contain A and B. It cannot contain any other points because otherwise it will have intersection 2 with
Okay.
either L or L dash. So in
Right.
this way, we'll say that all the other sets will have to be of size 2.
Mm,
Mm,
all the other set
ma'am,
will have to be. Then what is that? Okay, if they are of two size, then what is the claim? I did not
um,
understand. Right?
ma'am,
Yes. Any other?
what we can say is like using P0. If we take any four
Right.
element set, so
Right.
like
Mm-hmm.
with L1 there
P0.
has to be the intersection should be less than 2. With L2 it should be less than 2. But
Right.
also that like L1
L
intersection L2 is
intersection.
also 1.
And
Um,
L intersection. Sorry, L dash intersection F.
ma'am,
That will
so
also be
like
less than 2.
if
Right.
we
Right.
call the
Yeah. You
four
need to.
element
You
set,
need. Right.
if
So
if
someone
we
is
call the
talking.
four
Right.
element set ABCD, yeah, yes, ma'am.
Mm-hmm. Mm-hmm.
If we call the four element set ABCD, so
Okay. A B C D. Right.
so
So let's say
we'll
these are
face a
the four
problem.
elements. Say. Hmm.
We'll face a problem only when like L intersection F is AB and L dash intersection F is CD. Um,
L intersection.
because
Okay.
otherwise one of these 4 points would not lie on any of these lines.
Okay. Right.
But
So you
this
are in
cannot
correct
be.
direction, Sabon. Yes. So
But this
yeah.
cannot be
So
possible because L1 intersection L2 is also 1. So then 3 points would lie in a line. Um,
okay.
what I
Okay.
mean is one
So
of these 4 points will not lie on both of these lines. There has to be one point of these 4 points which would not lie on any of these lines.
okay. So So you are in correct direction, Shravan. Maybe yeah. Let's try to prove it formally. So what is the Thanks, Shravan. So yes, you need to actually apply the first axiom P0 means there exist 4 points, right? No three of them are collinear. So if uh, if it is the thing that L union L dash is not F, right? Then of course you know that there exists one point which is not inside any of these line, right? L and L dash,
Uh,
right? Then
excuse
you
me, ma'am.
don't need to. Yes. Yes. What is
Ma'am,
your question?
can we say directly that like in these four elements set, if I take one of these points to be the intersection of L1 and L2,
right?
So suppose
Yeah.
that A is the intersection of L1 and L2, then
Okay.
I can
Okay.
assume that B will lie on
Okay.
L1, C will lie on
Someone,
L2.
please hold on. Yeah. So if in this way, if you are going, then maybe nobody will be able to understand, and we will not be able to finish the today's plan. Okay. I think you are in right direction. Please hold on. So what is the thing is, so as I mentioned, right? If you see that L1 union L dash, L union L dash, uh, intersection F, right, is not, I mean, if F is not contained in L1 union L dash, then you know there exists one point which is outside this line. Then we have nothing to do, right? Otherwise, F is contained in, let's say, in this, right? Okay, how it can be contained? Let's see that thing. So we know that L intersection F is less than equals to 2, L dash intersection F is also less than equals to 2, right? So it should be the case, if this is the case, then it should be that I have line L which is passing through AB, another line L dash which is passing through the rest of the rest 2 points, right? That's the only possibility. Or maybe AC, BD. So without loss of generality, just consider that L is passing through AB and L dash is passing through CD. Without loss of generality, I'm just making this, okay? Okay, now consider this line. I am just referring this line to be L1, another line to be, sorry, again I am giving wrong number, L1, and this is, let's say, L2. So L1 is actually passing through AC, okay? And another line, L2, you can always draw by joining the point B and D, right? And these two lines will intersect in one point. Let us name that point as X, okay? And my claim is X is actually not belonging to L, and it is also not belonging to L dash, okay? That's the proof. And now the question is my claim correct? So do you understand what I am saying? So first I claim that F if F is not contained in L union L dash, then we don't have to do anything. Otherwise, F is contained in here, right? So if that is the case, and we know that this is the property of axiom 0, right? So using that property, we know that L is passing through 2 points and L dash is passing to other 2 points. That's the only possibility, right? So I have named in this way. And so what I am doing is just I am considering the opposite lines, AC and BD, right? So these are 2 different lines, right? So and according to our axiom 1, right? So they are supposed to meet one unique point. That point I am naming as X, right? And right. And my claim is this point X is actually not inside L and L dash, right? If it is, let's say it is for a contradiction, if it is in L, then that should be A, right? In that case, you know that there is one point which is actually common to both L and L dash, right? I mean, in this intersection, and there is one point which is left out, right? So among these 4 points, one point is left out, right? Similarly, the other case also, right? So this statement is done. Now the left out is this part. You need to check the bijection, I mean the function whatever I define from L to L dash using this projection, that is a bijection. Can you prove it quickly? Then our we have this proposition, right? So can you prove such statement that this function is a bijection? Quickly. Okay, this is also very much straightforward, right? So what you have, so you understood that I mean, if you consider any point y, right, that will uniquely map one point in Z. That's for sure. Now consider any point Z, right? And let's draw the line xz, right? Maybe that might be different line if you want to say. That might be. I don't know. Okay. So the picture was like this, right? Okay, what was the picture? I forgot. Let us do the picture. So I have x here. I have one line L, another line. Let's say this is my L dash. So I just took one point from y, right? So and I just project that xy into L dash, and let's say that is my z, and that was my bijection. So right. So I will this function will take y to z, L to L dash. Right. So now consider any any arbitrary point z, right? So now if you draw this line xz, if you draw this line xz, okay, so you will get one unique line, right? That line is also it should intersect the line L, right, somewhere, right? Now we need to show that this point is same as the point y, right? Or in other word, the line xy and xz, they are actually same line, right? If you can prove that, then that is done. So why they should be the same line? Why they should be the same line? Again, it comes from the properties. If you see the property, right? Axioms.
Otherwise, two lines will intersect at x and z.
Right. Okay, so you have understood, you are convinced that this function is a bijection. So the property, I mean, now basically it's if it is a bijection, then you can straightforward say the cardinality of L is basically cardinality of L dash. Okay, does it make sense? Okay, this is very surprising fact, right? So if you have a finite projective plane, then every line you have, so that's the thing which we saw in phanoplane also. Phanoplane was a finite projective plane, so you saw that every line has 3 points, right? Every line, right? Okay, good. Now let us define order of a projective plane. Okay, so what is the order of a projective plane? Order of a finite projective plane is actually the number this. Means so you consider any line in a projective plane, and you know that all of the line has same number of points, right? So let's say it has some number L, L cardinality of L minus 1. That is basically your order of the finite projective plane. This way we are defining. Okay. The order of a projective plane, finite projective plane is basically the cardinality of each set minus 1. Okay. So what is the order of this phanoplane? Can you tell me? So order of the phanoplane is basically 2. Okay. And it's the smallest. That's why I told you it's the smallest possible finite projective plane. So order 2. Okay. Okay. Very good. Now let's come back to the main theorem. So what it says, let's say I have a finite projective plane. Then we should have such things. So what are the things? So we are saying that you consider any point, okay, in your finite projective plane. So it should pass through exactly n plus 1 line, right? N plus 1 line should pass through that point. You consider any point, and this is true for every point. For example, if you see the phanoplane, so here you can see each point is passing through exactly, 3 lines, right? Right? That n plus 1, right? N plus 1 means the order plus 1. So 3 lines it is passing through. So not only that, what is the size, what is the number of elements or number of points you have in the finite plane, that also you can count, and this is this number, n square plus n plus 1. And surprisingly, the number of lines are also same. As this number means cardinality of x is same as cardinality of, okay, this should not be L. So this should be basically cal L. Okay. So number of lines, basically number of lines is same as, this is wrong. This should be L. I'll make a correction, and I'll before uploading it. So number of sets in your finite projective plane, that is exactly equals to number of points, or in other words, number of points and number of lines are same. Okay, so let's try to prove these one by one. Let's try to prove the first statement. Means there are exactly in, I mean, if you consider any point in X, it should pass through exactly n plus 1 lines. Exactly n plus 1 line should pass through that point. Can you prove this statement? How will you prove such statement? So for example, if you see the plane, right, we saw that every point is passing through exactly 3 lines. So how will you prove such this thing? N plus 1 line is passing through. Any idea? Okay, again, I am just giving you first hint how to prove it. Then you can complete the proof. Okay, first we are claiming that there exists a point. There exists, consider any point, okay? X in X. Okay, this is that X, let's say. Claim is you will be able to find one line which does not pass through this point. Okay, there exists a line in this such that X does not belongs to L. Okay, can you prove this statement? So if this is true, let's say for the time being, let's say this is true. Okay, so this is my L which doesn't pass through this point X. Okay, so what I will do, so I know that this line L has how many points it has? We know that, right? We consider that it's a finite projective plane of order n. So it should have n plus 1 many points, right? Right? According to the definition and according to the proof which we had. So it should have n plus 1 many points in it. Okay. Right. So let's say these are nothing but x1, x2 up to xn plus 1, right? And now I can draw always a line like this, like this. These are all unique lines, right? So I have drawn, how many lines I have drawn? How many lines I have drawn? N plus 1 many lines I have drawn, right? Okay, so I can see that at least n plus 1 many lines are passing through this. Now, why this is at most? Can you tell me? So why this is at most? So you can see that there are n plus 1 lines, right? If this assumption is true, if we can prove that there exists one line which actually doesn't pass through X, then this is very straightforward. Okay, so I assume this. With this assumption, we show that, okay, you can readily see that you can see readily that n plus 1 lines are there which is passing through this. Now the question is, why all the lines, whatever it is passing through X, they are actually of this type? Okay, is it possible that there is another line which is not counted here? Is it possible to
We
have
can
another
consider
line?
that there exists such a line, and then we'll have intersection with the original line L.
Right. Thanks, Shanta. Yeah, argument is correct and exactly correct. So let's say I have, as Shanta said, so let's say I have one line. Let's say that line is L dash, some line. Let's give that L dash, right? Which is not counted in this count, right? So if you consider this line L dash, so of course, according to our assumption, means according to our finite projective planes definition, it should intersect L, right? Some point, right? So in this, this point, where is this point? This point should belong to this one of these points. So it is already counted in your count. So you don't need to count this, right? Twice. Good. So that's why you have exactly n plus 1 line passing through every point in your finite positive plane. Okay. So the only assumption which we made to prove this is this one, right? That there exists one line which does not pass through X. So can you prove such statement that you will always be able to find such point which does not pass through this? Can you prove such statement? How will you prove? How will you prove such statement?
Okay, let us just draw all the lines, and then we'll take two different points from two different lines.
Okay, let us take What you said? You want to
Like
draw?
this is the common point, no, for all the lines.
Acha. So right. Okay. You want to say this is the common point for all the lines?
Yes, ma'am.
Okay.
And then we'll take any two lines and take 2 points on them, like AB. Because we
Acha.
need to have at
AB.
least 4 points, there exist at least 3 more points. So AB.
Acha.
And then there exists a
A.
line that joins 2 of them. And then X
Okay.
also must lie on that line.
Okay, so in other words, actually you can state yes, yes. You in other words, again you need to see this property P0 to prove this, right? So my battery is low. So what I can do, maybe I don't know whether you will be able to see it. What I'll do, I'll plug this machine. So sorry for this, huh? Plug this machine to directly to the charger, but okay, can you see? Maybe you will not be able to see me properly. Okay, anyway, I'll try. Am I visible? I think I am visible, right? Okay. Yeah. Okay, so you need to utilize the property P0 for this, right? So so you know that there is F, right? Okay. So from using this property P0, can you prove it? That there should be one line which doesn't pass through this point X. Okay, let's consider this. So F has exactly 4 points and they are distinct, right? So it should be the case that if you have some point X, right, you will always be able to find 3 points from F which are distinct from X, right? Let's say those 3 points are A, B, and C. They are distinct from X. They are not same. Okay. Okay. If that is the case, basically, then what can you say? From here, can you say something? That there exists one line which does not pass through. Can you construct one line which does not pass through X?
Line
Combining
through
this
AB.
line through AB. So I have line like AB. Okay. So this is, let's say, AB. I have line like AC, right? Let's say I have line like this, right? Now what can you say? Is it possible that X is lying on both of them? Okay, from there you can't say, right? Can you say this, that X is not passing?
Already A is the intersection, so X cannot
Right.
lie on both again.
X cannot lie both AB and AC for sure. Okay. Right. So it right, from there you can find one line, right? X is not containing both AB and AC. So right. So one of the line is not containing X. So from there you have one line, right? So it's straightforward. Good. Okay. Very good. So so we have proved this statement, right? So there exists one line for any point you choose in your plane. There exists one line which doesn't pass through X. And if that is true, then basically using this line and the point, right, you can draw all the possible lines containing those points in that line, right? And these are exactly n plus 1 many points, and that gives you the proof. Okay, very good. So this proof is, again, as I said, it's a very straightforward proof. We don't need to do something fancy here. Okay, now let's see. Oh, so sorry. Now let's try to prove the other statement. The other statement means, let's say I want to prove the second statement. How will you prove such statement? Cardinality of X is n square plus n plus 1. Okay, how will you prove such statement? Can you prove it? That there are exactly this many points in your system, not more, not less. Can you prove it quickly? Any idea? Okay, I am giving you again one hint. So again, the previous proof, actually from that previous proof you may try. That's the hint.
Consider all the sets containing one particular point.
Okay, right. Yes. So that's the proof. Basically, so consider any point X, right? And any line that doesn't pass through X. I know that you will find such, right? Such line and such point. For any point x, I have such line which doesn't pass through x. That we proved last, right? So, and we know that if you consider all these points in L, means there are exactly n plus 1 many points, you can draw these lines, right? Let's say L, this is passing through x1 of the point in L. So I have n plus 1 many points. So this is x2, and let's say blah blah blah. I have this is x n plus 1, and let us say these are my lines. I am giving them also some number L n plus 1. So n plus 1 many lines are there, right? Now if you count all the points contained in all these lines, right? So how many elements are there in X? At least how many elements are there in X that you can have, right? So what is? Can you give me the count? So you can see that there exist at least. So in L1 I have, apart from this X, this point, common point, I have exactly n plus 1 many points, right? So similarly for L2, similarly for any Li, right? So in this, each of these n plus 1 lines, I have, apart from x, I have exactly n lines, sorry, n points. And of course, you need to count x also. So you can see the cardinality of x is at least this, right? And which is basically the number n square plus n plus 1. Okay. Now you need to show that, okay, x cannot be more than this. Then you are done. Cardinality of x cannot be more than it. You have shown that the cardinality of x is at least n square plus n plus 1. You need to show that all the points in your system that you have counted here, there is no point left out, right? If that is you can do, then basically you are done. So can you prove such statement that there is no point left out over here? Can you prove such statement? Again, it is similar to the proof for the proof which we did in the last proof, okay, in that same line. Can you prove it that there is no point left out in this counting? Can you prove?
If we consider any other point y, then there exists exactly one line containing x and y. And since exactly n plus 1 lines pass through x, the line passing through x and y must be one of these.
Right. So that's the proof basically. So in other words, so what Shubhan said, let's say I have a point here, okay. Let's say this is that new point which is not counted here. Let's name that as x. Sorry, y. So of course we can draw one line xy. Okay. Of course you can draw one line xy, right? And that xy will definitely intersect the line L, right? So in other words, so this line is already counted here in this L1 up to Li, Ln, whatever the line we had, among them only this line should be there, right? Whatever you had, right? You had n plus 1 many lines. So among them, this line will also be counted, right? So in other words, there is no such extra point outside the count which you have given, right? So in other words, the cardinality of x is exactly n square plus n plus 1. Okay. Okay, so that's done, right? Okay, now let's consider the third proof. Okay. So what is the third proof? Sorry, third statement, right? What is the third statement? So we are not going to prove it right now. Maybe the proof we will see the proof by consequence of some other fact. Okay, so the number of lines is exactly same as the number of points in your finite projective plane, right? So that we will prove via duality. Okay. Okay, now let's see what is duality, what type of duality we are going to define here. So let's consider again the finite projective plane. So you have a finite projective plane, right? So you have what is the meaning of finite projective plane? So it should satisfy the property which is given to you. You have a set of points, you have a set of lines, right? Now, given a finite projective plane, so dual of that finite projective plane is something like this, where you are considering your point as a line and the line as point. Okay, means you're interchanging the role of points and line. Okay, if you are doing that, then you are whatever you are getting, that is the dual of the given finite positive plane. Okay. Another question is whether, I mean, this the dual whatever you have understood, right? For example, let's say you have a plane like this, right? So I have one line like this. So I'll consider in the dual this line as my point. Okay. And the point as a line, as I mentioned. So how can we point as a line? Okay. So if you want to construct, if you want in the dual, point is becoming one line. So how it can be a line, right? How? So you should define properly, right? So what I am saying, that the lines whatever it is passing through in the original plane, right? So consider that as your element in that line. Okay. So okay. Do you understand what I'm talking? If not, it will be more clear once we learn incidence graph. Okay, let's see the incidence. What is so? By the way, so do you know what is incidence graph? Do you see this term before?
No.
Incidence graph you did not see. Okay. Acha, okay, no problem. So I will explain what is incidence graph is. So incidence graph is basically, so if you remember, finite projective plane is basically pair, right? It's set of elements and a subset of that, right? A family of subset of that. L is basically a family of subset of that. Okay, so incidence graph is basically, it's a bipartite graph which represents the belongs to relationship. Means in one side you are going to, so it's a bipartite graph. In one of the, I mean, you know what is bipartite graph, right? Do you know what is bipartite graph? Or I think all of you know, right? It's a very standard thing. Yes, good. So this is a set of lines here, and this is a set of points. Sorry. This is a set of points, means the elements, and this is a set of lines, let's say. Okay. Right. I know that, okay, for finite projective plane, these two cardinalities are same. That's a different issue. But what is incidence graph? So incidence graph is basically, I will give x belonging to x and some line L belonging to this L, one edge in between, if x belongs to that line. Okay. So for example, if you see here in this plane example, the incidence graph is basically, in one side I have 1, 2, 3, 4, 5, 6, 7, which corresponds to points, right? And A, B, C, D, E, F, G, they are corresponds to basically the lines. Now you can see one is incident to how many lines, right? It is incident to line A, right? It is incident to line C, right? And it is also incident to line E. Okay, A, C, and E, right? This is the line E, this is the line C, this is the line E. Okay, so I have given edges from A1 to A, 1 to C, 1 to E, right? So the belonging relationship, whatever we have, so that is actually captured by this incidence graph. So, and it is true for all other point in X. Okay. So similarly, if you consider any line over this side, so you'll see the edges are basically, it's coming from those elements that is contained in that line. Okay. For example, if you see the line 6, right? 6 contains basically line point, oh sorry, 6 is not 6, I should not say 6, right? I should say C. For example, if you see the line C, right? This is my line C. So it contains exactly how many points? It contains 3 points. It contains, and which are those points? Those are basically 1, 6, and 5. So you can see, so 1, 6, and 5, they are adjacent to C, right? So this graph is known as incidence graph. Okay. So incidence graph, it's not only you can define it for with respect to any set system, not necessarily with respect to finite projective plane. You can define it with respect to any set system, right? So I hope you have understood incidence graph. Is there any question on incidence graph? Is there any question? This is very straightforward, right? Okay. Now, what is the duality, right? The meaning of duality. So meaning of duality is something like this. Now, I am converting, my incidence graph remains same, right? So now I am referring this set which was earlier point. Now I am referring that to be my new lines, and the original line whatever I had earlier. So for that set I am just telling them that this is my points. Okay. So the role is interchanged, but the incidence graph remains same. Means this is the incidence graph. Whatever we have the graph earlier, that graph is same. Just the role of line is now the point, and the role of point is now line. If you change that, so then again you are going to get one set system, right? That might not be finite projective plane. I am not claiming that right now, but you are going to get another set system, right? By changing this. So for example, right now, so you can see what would be the line corresponding to C. C is now going, so sorry, C was earlier, it was line, right? Now it is going to be a point, so we don't need to worry about it. It is just a point, right? This is my C. And what are the, okay, now let's see, earlier some point was there, now it is becoming line. So what is that line? So for example, 1 is now a line, right? So what is that line? So now you have this, you can draw this A, B, let's say this is C, this is D, whatever you have, F, 6, 7 are there, right? A, B, C, D, E, F, G, right? So now let us consider the line 1, right? So what is my line? This is corresponding to line 1. So 1 actually, it should contain A, C, and E, right? So A, C, E, this line, right? This line I am referring as 1. Okay. Similarly, corresponding to the point 2, I would have a line in its dual. That line is basically, you can see it is A, then D, then basically it is G. So it is A, D, G, right? So if you draw this, let's say I'm coloring this with another color, A, D, G. So this is my line number 2, right? So I hope you have understood, right? So this is the duality which I am referring as. Okay. Now the claim is, this is my big claim which we are going to do. The dual of a finite projective plane is again one finite projective plane. I hope you have understood the dual of a finite projective plane, right? Is there any question on that? I think the point is clear, right? How we are making a dual of a finite projective plane. Given any finite projective plane, what I am just going to do is basically I am changing the role of line to point and the role of earlier point to my line, and maintaining the incidence graph, okay, appropriately. Then that would be my dual. So if you understand the duality, so you can see dual of a dual is the original finite plane, right? Finite positive plane, whatever you have. If you just make 2 times dual, right? If you just perform this operation, duality operation twice, then you are actually coming back to the original finite positive plane, right? So dual of a dual, I mean, if given a finite positive plane, if you just construct dual of dual right? Then that will be the finite positive plane itself. There is no doubt about it. But the claim is, if you just take one dual, right, you just perform this operation once only, then also whatever the set system you are going to obtain, that is again going to, it is again one finite positive plane. Okay. Now the question is, why is so? Can you prove that this property? This is true thing. I am not bluffing you. This is going to be the same thing. First of all,
properties hold.
Right. So we need to show that all the properties which we mentioned, P0, P1, and P2 earlier, right? They are actually satisfied, right? Okay. So we need to show that them, right? Okay. So start with property P0. So that's the only way to prove, right? If you want to prove that dual of a finite positive plane is a finite positive plane, so you need to ensure that these properties are satisfied. Okay, Mrityunjay correctly pointed out. Good. So P0, you need to show P0 is holding. So how to prove that P0 is holding? Can you? So what statement first of all we need to prove if we want to prove that P0 is holding? Can you tell me quickly? Okay, so as I mentioned, right? So points become lines, right? In the dual, and lines become point. So if you want to satisfy this property with respect to the original plane, so in the original plane, what we have to prove, right? So in the original plane, we need to prove. So in the dual, we need to prove that there exists 4 element set, means there exists 4 points, right? Such that no 3 of them are collinear, right? So what will be the dual statement? There exist 4 lines such that no 3 of them are intersecting at one point, right? In the original plane. If that is true in the original plane, then in the dual that would be the thing, right? So we need to prove this statement. There exist 4 lines, let's say L1, L2, L3 and L4, such that no 3 of them are coinciding, right? So coinciding, should I write? Intersecting at one point, right? Coinciding, I think that is okay. Intersecting at one point. So you will be able to find. So in other words, you need to show that you will be able to find 4 lines in the original plane, in the original finite positive plane, such that no 3 of them are intersecting at one point, one common point, right? So if that is true, then automatically you can consider those lines to be your 4 points in the dual, right? And since they are non-intersecting, if they are not, it's no 3 of them are intersecting at a point, means no 3 of these points are actually collinear, right? Okay, so how will you prove that this is going to happen? This is true. How will you prove such statement? How will you prove?
Yeah, can you consider the 4 points in P0, that ABCD?
Right. That's the correct guess, and I should say that's the correct approach. Yes. So how will you do this? Yes, you have correctly pointed out. So consider the 4 point A, B, C, D in F. Okay, you know that F is there, right? This and they satisfy the property P0. Now you need to construct 4 lines out of these points, right, such that they satisfy this property. Now the question is, which of those, how will you construct those lines? So let us consider line, okay, right. So let us consider line passing through AB, another line, let's say, passing through CD, okay. Let's consider this my L1, let's consider L2 to be CD, and L3 to be, let's say, AC. No, sorry, let's say this is AD, okay, passing through AD, and L4 to be BC, okay. And my claim is these are the 4 lines which satisfy this property. Okay, that's my claim, but you need to prove it. So I said that, okay, out of these 4 points given in F, I have constructed 4 lines like this, okay. And my claim is these 4 lines are basically satisfying the property. Why so? If that is the case, why it is so? That if you consider any, okay, so let's say this is my AB, this is my CD, this is my AD, and this is my BC, right? Okay, so this is the picture. I draw the picture also for you. Now, can you tell me why is so? That no 3 of this is passing to one point. Why this is true? Why this is true? Okay, so you need to prove it by, okay, let's take any 3 of these lines. So maybe, okay, let me draw it with some different color. Let's say this. Okay. So let us consider any 3 lines arbitrarily I'm choosing. Let's say this is that. Okay. Another one, which line would you like to prefer? Maybe another line is this one. Okay. Third line is this one. Okay. Any 3 line you choose. Okay. Okay. You can see these 3 lines, whatever you have chosen, AB, AD, and CD. Among these 3, there are 2 lines which are intersecting at one point, right? And that point is inside F, right? For example, if you consider AB and AD, they are intersecting at A, right? So is it possible that CD is again intersecting at A? Is it possible? CD is again intersecting at A? It is not possible, right? No, it is not possible, right? It might intersect somewhere else, right? Not here, right? So AB, AD, and CD, they are not passing through one point, right? Right. So if it was the case that AB, AD, and CD were passing through one point, then that point should be A only, right? Not other point passing through one point. So it's not true here. And you can check for other any 3 lines. If you see using that same argument, you can actually say that it's not possible for them that 3 points are passing through one single common point. Sorry, 3 lines passing through one single point, common point. It's not possible, right? So, so my claim that L1, L2, L3, L4, the way we have constructed, it is actually satisfying this property, right? So that's my so if you just take the dual of them, means if you consider these lines, whatever you have considered over here, and convert them into point, right, in your dual, right? So then they will satisfy the property that no 3 of them are collinear, right? And that's the property which is required. So P0 is done. So in this way, you have proved that the set system, whatever you have obtained by performing the dual operation, they satisfy the property P0, right? There is no doubt about that. Okay, now let's try to prove P1 and P2. P1 and P2, is it very much obvious? We don't need to prove anything, is it? Okay, let's try to prove P1 in your new set system, right? So if you want to prove P1 in your new set system with respect to the original set system, means with respect to the finite projective plane, the original thing, what is the property you need to prove, right? So you need to prove any 2 okay, you need to in the dual plane you need to prove any two distinct set like this, right? Such that they intersect in exactly one element. So in the dual, it would so the dual of this statement is basically any two distinct element, right, passes through exactly one line, right? That should be the property with respect to your original plane, which you need to prove, right? And that property is exactly P2, right? Right? We know that P2 is already in with respect to the original plane. We know that P2 is already there, right? So we don't need to prove anything extra. Similarly, if you want to prove P2 for your dual, right? The statement which we want to prove in the original plane will be this one, right? P1, which is already true with respect to the original plane, right? So you don't need to prove anything extra. So P1 and P2 are dual of each other. These statements are dual of each other. So in other words, our claim that, sorry, so what was our claim? So our claim that dual of a finite projective plane is a finite projective plane, okay, that is actually true. That's actually correct, okay. Okay, I hope you have understood the duality and the meaning of this statement, right? Acha, okay. If you buy this duality and if you buy that, okay, dual of a finite projective plane is again a dual, then let's come back to the theorem which we did not prove and which we said that, okay, we are going to prove it by duality. So you can see that this projective plane, whatever it is given, if you take the dual, then this number of line is going to be actually the number of points in that dual, right? And that dual is actually a finite projective plane, right? And okay, so the number of points is becoming line means this statement is again actually true there. So basically, you got as a byproduct of duality, right? This third statement, we don't need to prove anything. If you have the duality, it is just straightforward. Okay, because line is actually playing the role of point over there, right? And you know that dual of a finite projective plane is again one finite projective plane, right? And with respect to finite projective plane, we have proved that property, that 1 and 2 property is already proved. So we don't need to do anything else, right? Okay, very good. I hope you have understood. Okay, we have some time. That's good for us. Okay, now let's now let's come back to affine plane. Okay, it's okay. The affine, let us define it. So it's very similar to finite projective plane. There is only few differences. Okay. First of all, so what is affine plane? So affine plane is basically, again, it's a set system only. Okay, you have a finite set of element and a family of subset or system of subset of X, and the pair X comma L is actually, oh, I am sorry, here I did not change it. It should be affine plane. Sorry, it should be affine plane. I'll change it. Affine plane. If it satisfies the following properties. What are the properties? So again, so here basically I should write every two not points elements are incident with a unique line. Okay, so every two elements, if you consider, right, like this property is actually true also for finite projective plane. If you consider any two distinct point, there should be a line, right? So that's the meaning of this property, which is also true with respect to finite projective plane. Okay. I see. Okay, I am so sorry. Actually, I did not write it properly. These are wrong properties which I mentioned here. Okay, I see. अच्छा ठीक है. ठीक. This is right. This property is right. Okay, ठीक. Okay, so what I am saying. Okay, so this is one property which is actually common with finite projective plane. There is another property which is similar to finite projective plane. It's not same. So what we say, right? There are 3 points such that no three of, I mean, there are 3 points which are basically not collinear, right? So that's the meaning of this. There are 3 points which are not collinear. Okay. So this property is there. It's a slightly deviated property from the property which we have for finite projective plane. And what is the third property? So third property is basically if you consider any element x, okay, and one set L such that x does not belongs to L. Okay. If that is the case, then you will be able to find one unique set M in L such that x is actually belonging to M. And not only that, if you are going to take intersection of M and L, then that should be basically empty. Okay. So this is somewhat interesting property. So in other words, what we say by this property is something like that. We want to say, convey this. So you can understand, right? M and L intersection is empty. So it means M and L are basically parallel line. Okay, that's the meaning basically. So if there exists one point which doesn't go through one line, then you will be able to find out one line passing through that point which is basically parallel to this line. Okay, so that's the extra or something different property compared to finite projective plane. Means this property is basically, it's similar to Euclidean plane, right, where you allowed parallel lines, right, which was not allowed over finite projective plane, right? In finite projective plane, what was the property? If you consider any two lines, they should intersect at a point, right? So in Euclidean plane, it's not the case, right? You might have points which are basically parallel, right? They don't meet each other. Similarly, affine plane is actually it's capturing Euclidean plane in some sort. Okay. Okay, example of affine plane. Let's see. This is one example of an affine plane. You can see these are parallel lines. Okay. And not only that, I'll change the color. Okay, I know that the color, even if I change the color, it is not. Okay, this, they are also parallel to each other. Okay. And what else? So can you see that there are other lines also? Those are parallel. There are other lines also who are parallel. Can you see that? Okay, now let's see that whether our properties are satisfied. So can you see that there exist 3 points which are not collinear here? Can you see that there exist at least 3 points which are not collinear? Means F is there, right? We should have F over here. According to this definition, F is basically a set of points. Okay, I'm so sorry. Okay, I don't know how to do this. Oh. Something wrong, right? Okay, I need to go back here. Okay, so my question was, so do you see that there exists 3 points over here which are not collinear? Can you see it in this example? So question is, can you see that all the properties of a affine plane, whatever we have mentioned there, so they are basically satisfied in this figure? Can you check it? Every 2 points are incident with a unique line. Can you check it? You consider any 2 points, they are incident to a unique line, right? That property is satisfied over here. Now, if you consider some element which is not in a line, for example, let us consider this point, and this line, right? You can see that this point is not lying in this line, right? Now the claim was there should be one line which is parallel to this blue line and which is passing through this blue point, right? And that is true, right? You can see this line which is passing through this, and they are parallel, means they don't intersect. There doesn't exist any intersection, right? Okay, so this property you can check it for all other points, every other points which satisfies such thing, and you can verify it. Okay. And now the question is, what are the 3 points such that they are not collinear? Okay, that you can find. So you can see this point, and let's say you can take arbitrarily some other point, right? For example, are they collinear? Are they passing through one point? No, right? They are not passing through. So maybe you can find more. Means these are analogy of Stovall here, right? You can find more. It's not unique. Okay. Now I have 2 questions for you. I'll just conclude with that question. First of all, can you prove that the relationship that we are here actually in the affine plane, this relationship that one line is parallel to other, right? This relationship is basically it's an equivalence relation with respect to affine plane. Can you prove it? Just it's just homework. You just try to do this. Means if you consider the lines, right, given here, and if you consider that one line is, let's say x is parallel to, sorry, let's say it's line L1 is parallel to L2 and L2 is also parallel to L1, then L1 is also parallel to okay, L2 is, sorry, this L3. L1 is also parallel to L3. Can you prove this? Can you prove that the relationship parallel line relationship, that is basically equivalence relation, and it will actually partition your set of lines into equivalent classes? For example, here it is true, right? This is one class which are parallel to each other. Similarly, you can draw this set of line which are parallel, right? Similarly, you can draw this line which is parallel to this line, right? Okay, let me redraw this drawing. Maybe I need to check this. Yeah. So, for example, right. So, if you consider this line and this line and this line, they are parallel to each other, right? So, in this way, you are getting some class, right? So, can you prove that this parallel relationship is basically one equivalence relation? So that's one question. And the other question which I would like to ask you, can you convert one affine plane to a projective plane? So you can see that affine plane is not projective plane, right? So this plane is not satisfying the properties of projective planes, right? So can you convert one affine plane to a projective plane by some fancy way? Okay. And also another question is, given any projective plane, can you convert it into affine plane? Okay, think about this. Okay. Yeah, so maybe I can give you some hint. Given one projective plane, I'm just telling that you just remove one line and all the points incident to that line. Then that projective plane will become one affine plane. Okay, that's my claim. Just to verify that whether this is true. And how to convert now one affine plane to projective plane, so that you can see, for example, here for the illustration. So I had one, quickly I'll just a minute, yeah. So I had one affine plane. So as I said, you need to show that they are you have this equivalence class corresponding to these parallel lines. So with respect to each equivalence class, right? You just construct one new line, new point, introduce new point, right? So there were four equivalence classes, right? And 4 points over there you have introduced, and you are introduced one new line passing through all these new points, right? So which is line at infinity, I will refer as line at infinity. And each of the line belonging to this equivalence class, right? They have, I said, I have new point. So add that new point to all the lines belonging to that particular equivalence class. Okay. For example, this line earlier we had only 3 point. Now I am going to add so I have introduced one new point corresponding to these 3 lines, right? So, and I am ensuring that all these 3 lines are actually passing through this one extra point, means that point at infinity. Okay. Similarly, for this equivalence class, I have introduced this new point, right? And similarly for this, I have introduced this, and similarly for here, I have introduced this, and then these are you have extended it, right, until infinity, and you are assuming that in the infinite I have 1 point, right? And those points at infinity I am considering at a line, as a new line. So if you are going to do that, then basically affine plane becomes one projective plane, right? So that's the transformation. And if you have that, then basically these are the properties which is very much straightforward, and one can prove directly from the properties which we have proved for finite projective planes. Okay, so what are the properties? For example, if you consider any affine plane, right, you will see that every line is incident with a constant point, n many points. Okay, every line is incident with n many points, and every point is incident with n plus 1 many lines. Okay, that's the difference. So here we are actually, if you remember, we define the order of finite projective plane. So similarly, one can define order of affine plane, and here we are actually defining this n, means every line contains that n many points, right? So that n to be the order of the corresponding affine plane. Okay, if that is the thing, then basically one can verify that any affine plane of order n has exactly n square many points and n square plus n many lines. Okay, I am not proving it. I am just leaving this statement, this statement, not 3, right? Right. Sorry, this statement basically, to be specific, this statement. Just try to prove it. Okay, using the whatever you have learned so far, using the properties of finite projective plane. Okay. Okay, I think that's it for today. I think we are being late also today. So, do you have any question? Do you have any question? Any question? So, just try to build your own proof for these affine planes, which is very much similar to finite projective plane. Okay. Any question? So, if no question, so let's meet again on next Monday. Okay. All right. So in the background, maybe what you should do, at least you should try to brush up your knowledge regarding this modular arithmetic. Whoever who knows modular arithmetic, and those who know finite field, just brush up those knowledge so that we can utilize it for constructing finite projective planes and all. So those things. I mean, if you, for example, so far we have only discussed about properties of finite projective planes, right? Some of the beautiful properties. You can see those are very much, I mean, they are regular, right? So much regularity is in there. So the question is, how would you construct finite positive plane? So it's not so much obvious. Given any n, you might not be able to construct one finite positive plane, right? So how to construct such thing, and when it is not possible to construct even, right? So those kind of thing, if you want to understand in detail, so I would actually ask you to have some knowledge in the elementary concept in finite field. Those who know finite field, or maybe modular arithmetic. That would be very much helpful. Okay, with that, maybe we can conclude today's lecture. If you have any question, maybe please ask me. Feel free to ask. Do you have any question? Any question? Okay, if no, let us conclude then. Thank you for your attention.